All right. So welcome everybody. This week we're talking about community detection in networks. And I don't know, for some reason I find this a particularly fun topic. So mostly I'm going to be using, again, the Stanford slides. I did a little bit of reading, around this, and so I'll have a few additional things that I'll reference and a few things that I thought were not necessarily completely clear um, uh, from the Stanford notes and lectures. So today we're going to talk about understanding communities and how do you measure community structure, which surprisingly there really isn't agreement. So we'll talk about one way of measuring it, but there are other ways that people measure, and it's not complete agreement. And then two, we'll go into the details of how two really interesting algorithms work. So there's the Louvain algorithm, which is, I don't know how old it is, but it's very widespread. And then there's a relatively new algorithm. I think the paper was published in 2019. This NOCD algorithm. And so that's kind of the outline for today. So barring any trolls, feel free to ask questions in the chat or unmute, and I will thankfully have Yan and Ryan acting as our moderators in case there's anybody who is so bored on Saturday that they just want to say inappropriate things. Okay, so first topic, understanding, communities. So we often, when we think about networks, we think of it like in this picture where you kind of have these tight clusters, communities, whatever you want to call them, with a spare number of edges connecting them, but highly densely connected within. And one of the questions is, why do we think of it that way? Is that an accurate way to think about community structure? And the answer is yes. And so how people have kind of thought about this is if you think about the information flow, okay, so imagine a social network, and so the nodes, the red dots, those are people. And now you've got sort of information flowing between people. What's typical is if you have a close-knit friend group, you're going to see each other all the time. And so there's going to be a lot of information that passes back and forth between these people who are very close to you. And then if you think about your, more acquaintances, whatever, then we can kind of think of those as being sort of longer distance links. But of course, technically speaking, in a graph, we have nodes and edges, and they're not labeled as such. So the picture on the slide shows them as sort of being longer, but a priori, there's no way to know whether a given edge is short or long. And so there's this research by Mark Granovetter, and this is actually, like 50 years ago. And he discovered some interesting properties that at the time were not completely obvious to people. So one of the things he looked at was, how is it that people, if they're switching jobs, how do they find out about a new job? And it turns out that what he saw in a lot of data was that the job that they ended up switching to, they heard about from someone who was an acquaintance, but not like a really close friend. And so intuitively, you might think that like your close friends who really like you a lot, they care about you more. They ought to be the ones who are giving you information about these like new job opportunities. So why is it that in the data they saw that no, actually, mostly it's not coming from your close friends. It's actually coming from people that you don't know as well. And so we can answer that question by thinking about it from the perspective of what we were saying about like strong and weak relationships. Okay, and so you have this very structural, tightly high degree connectivity within a group, and then weak connections, few long distance connections where you have somebody who's not, as a friend. But there's another way that you can look at it, which is that yes, um, in addition to having these strong bonds, sort of within your community, what we also can see though is that the information is highly redundant. that basically if you're friends with all the same people and they're talking to each other and they're talking to you, then basically you could talk to any one of them and they're going to tell you almost the exact same thing all the other ones have, that the information that they know is going to be highly redundant. Whereas when you look at these weaker long distance links, that's where you're actually seeing new information. And so that's sort of the reason. And so like in hindsight, kind of knowing this, it's sort of like, yeah, like if a whole bunch of my friends are people that I work with, well, how are they going to tell me about new job openings? Because we all work in the same company, we all know everything. But if it's somebody who I, don't talk to that often from high school, they may work somewhere else and say, oh, by the way, this job opened up at my company, or a friend, or something like that. And so that's the idea. So you can think of that as an intuitive explanation for why it is that information from these weaker long distance links may be more valuable. So another thing then that we can look at is from the perspective of how these social networks evolve, okay? And so one aspect is triadic closure, okay? So I think this has even come up when we've talked about sort of like link prediction, but basically, if B and C are both connected to A, then there's a much higher likelihood that a connection will form between B and C than if B and C didn't have somebody in common. And so, so that sort of that triangle that forms, that triadic closure, is a very natural thing. And in fact, you can even think about it from multiple perspectives. So one is that, okay, if they have this friend in common, they're more likely to just bump into each other because they have the friend in common. You could also think of it in terms of that they may trust each other, or they may have just like more things in common, because whatever they have in common with A, they then likely have in common with each other. And then I thought this third point was interesting. A sort of has an incentive to bring B and C together. So if A is my sports friends, and I'm sorry, if B is my sport friend and C is my classmate friend, I have to spend time with them separately in order to be with them. But if they just becomes friends with each other and then we're all friends together, then I could spend time with B and C just all at once without having to manage them separately. And so these are reasons to kind of like intuitively see like why there would be triadic closure. And so if everybody's doing this, then ultimately what you're going to get is these tight clusters with high degrees of connectivity. So so that's like empirically what we see, but then also some ways of thinking about it, understanding it. And so this study was written up, but it was pretty hard to like test it empirically until basically we had more data and faster computers. And so there's a study from 2007 where they looked at cell phone data. They got a whole bunch of cell phone data from Europe. It says here 20%, that's a lot. And so what they did was then they had this measure of edge overlap. So basically, this is sort of your intersection over union, kind of a thing. And so basically, it's just looking to see do between two nodes I and J, do we have a lot of neighbors in common? Okay, that's basically this metric. And so if you use this metric, then somebody who's in a tight cluster is going to have a higher number, and somebody who just doesn't have that, two nodes that don't have that relationship are going to have a much lower number. They may have a high degree, but they won't necessarily have friends in common. They might want to have neighbors in common. So if that's the metric, then you can take all the people who have phones and you can sort of do this analysis between pairs of them. And so this is what they found, is that basically the people who had the blue circles here, the people who had higher neighborhood overlap, so higher in the vertical direction, the y-axis, then they look to see, well, how many phone calls are there between these two people? And this very strong sort of linear looking relationship showed up on the blue circles, which is that the higher the degree of connectivity, the more total phone calls they saw on average between those two people. And then the lower the connectivity, the fewer. So they really confirmed that, yes, this pattern does hold, that if you have a higher form of clustering, it really does represent a stronger level of connectivity. And then just to really prove that this wasn't just some accidental natural property that always shows up, if you took this same network and you randomized things, so you permute all of the edge strengths in terms of the number of calls. So instead of the actual number of phone calls between I and J, you just randomly use one of the numbers from your pool of how many times people called. Then what you see is the red squares, because this is of course random. There's no there's no pattern to it whatsoever. So then the average degree of connectivity for people who had few calls and the average degree of connectivity for people who had a large number of calls, they're the same. It's flat. So this shows that the blue line really is fundamentally different from the red line. All right, so there's another example of this now. So this is, I'm trying to remember, what is this data? This is, I think, like some kind of, oh, this is the mobile call graph. Okay, so this legend you see here, the more red it is, that shows a higher degree of calls, and then at the other end of the color spectrum is yellow. And so it's a little bit hard to see, but if you see these long distance links, a lot of them are yellow. You do see some red or whatever, but it's actually kind of hard to tell what all the coloring is, because a lot of these dots are super close and you can't really see the colors that are connecting them. So what makes it really easy to tell the difference is they did the same thing here. They randomly assigned one of the valid strengths to the different edges. And when they do that, then all of a sudden this graph looks like this. And so I can kind of go back and forth, and you can see that, oh yeah, there's a lot more of the red in these longer links when you just do it randomly. But the real network here, it's a lot more yellow, because in fact, that is the nature of things, that you have weaker links for these longer distance links. There's a couple charts here that also, again, further just demonstrate this pattern. So the idea is, if you remove edges based on their strength, based on the number of calls, if you start by removing edges that have the weakest call strength, then what's going to happen is eventually you're going to start partitioning your graph into smaller and smaller connected components. And so this thing on the y-axis measures what's the size of your largest connected component. And what you can see is that if on the black line, if you remove high strength calls, then the size of your largest connected component breaks up slower. Okay, the size of the largest component is higher, whereas on the red line, which is below it, it breaks up faster. And again, this is because the high strength edges tend to be redundant. So A is connected to B, but A is also connected to B through C, through D, through other nodes. And so removing this link between A and B is not necessarily going to disconnect either A or B from each other. Whereas on these low strength nodes, you're more likely to disconnect things. And then there's another example of this here. I think this is, if I remember right, this is just another version again, where you can see that in this particular graph, removing the low strength edges dramatically broke things up the network faster. So lots of different ways of talking about the same thing. The idea basically being that it is appropriate to say that even if we don't have empirical data that measures the strength of edges, that simply if you look at the degree of connectivity, that is an appropriate proxy. And so our definition of communities is usually based something around structurally, are they densely connected, or are they sort of weakly, loosely connected? And so that's why we have this fundamental concept of, we think that in networks, there will naturally arise sort of these communities with highly redundant edges that we think of as being strong, even if they're not labeled as such. And then we think of weak edges as being the bridges between these communities. All right. So I feel like I went through that pretty fast, but hopefully it was fairly intuitive. Any comments or questions on sort of just community structure in general? All right, so then let's go to the next topic, which is actually identifying and, not the algorithm, but just measuring and identifying communities. So if we have this theory that says that tightly connected nodes are communities, how exactly are we going to measure that? We know that there's this idea of lots of internal connections and few external connections. Okay, so that's a nice idea. We'd like to use this in some way to automatically find densely connected groups. And so we have different names for these: communities, clusters, groups, nodes. So this is a little bit like clustering, you know, if you guys are familiar with like k-means or whatever. But of course, in the graph context, things are a little different because we have this fundamental graph structure that we're going to utilize to identify these communities. So there's a famous example. Apparently, somebody was studying this Zachary's Karate Club network. They were studying the social dynamics in this karate club. So they started mapping out who's friends with whom, and like basically like, you know, do they do stuff together outside of when they're in, you know, the karate class, club, whatever. But then this weird, amazing thing happened is while they were studying them, there was an argument, a rift built, and basically the club split into two, and half the people left the club and formed a new karate club. And so you can see this red line indicates sort of if you were looking at the degree of connectivity and you were trying to find sort of the minimal cut to split this into two separate, that would sort of be this red line. And what in actuality happened is the squares, you know, went in and were one karate club and the circles were another. And so it looks like there's this one node 9 circle that's mislabeled. But otherwise, pretty much the structure of the graph could have predicted exactly how the two new karate clubs would have turned out. So that's promising. So let's kind of like figure out, well, what is it that we're looking for? If you were to take the adjacency matrix for a large graph, and if you kind of sort it right, then what you're going to see is you're going to see sort of these squarish, rectangular patterns show up in the adjacency matrix, because, you know, this group, say the top, whatever that is, like 6th, basically, you know, they're all sort of highly connected to each other. It's not completely black. It's not a clique where every single node is connected to every other node, right? In this case, this is a graph of people buying ad time from someone like, you know, Google or whatever, for searches. So basically saying, oh, if the user does a search on this particular topic, these keywords, then I want you to show them my ad. And for these people, I don't want you to show my ad. And so then you very naturally see this sort of clustering activity. And so one way that it shows up well is like on this adjacency matrix. So if you see sort of this little horizontal stripe here that has a lot of dark, so this is somebody, you know, where a lot of different people, unrelated, all want to buy ads for this particular query term, you know. That's sort of the unusual pattern. Usually what you see is these sort of squarish rectangular patterns. All right, so if we look at this graph, this is a graph of college football teams, and there's an edge for each team that played each other. And like, if you squint, maybe it looks like you can find some areas that are a little darker, seem a little bit denser, but it's pretty hard. I mean, for me looking at it, it's hard for me to say. But if you crunch the numbers, then what you can do is you can ultimately say, okay, these teams, these nodes here really do have a slightly higher amount of connectivity with each other than they do with any of these other nodes. And same for the black, the red, this purple over here. And then if you do that, ultimately, and then you go and you peek, what you see, the ground truth is that in fact, these dots are now colored based on what conference they're in. And so this community detection algorithm pretty much nailed it. You can see that there's like a white node and a light brown node and another light brown node that look like they got misclassified. And then this, I don't know what this is, dark gray, got split in two. So other than that, it looks like it pretty much nailed everything. And interestingly, in college football, you have these independent teams that aren't actually in any conference. I'm familiar with like Notre Dame, they were, been independent for years. And so the algorithm actually said, well, I can't really see any pattern. It didn't put these. It got one of them wrong, but for the others, it actually kept them in their own little community, not automatically just throwing them in with one of the other ones. So how can we do that? So we want these tightly connected nodes, and so we're going to define this modularity metric, and usually what we use for modularity is the letter Q. Okay, so if you take a graph and you partition it a particular way, and the partitioning we call big S. And big S is going to be comprised of some number of communities, each represented by small s. So small s1, s2, s3. Then what we can do is we can measure the number of edges that are within each group. So between nodes that are within the same community, small s, and we can subtract the expected number of edges within that group. So you can say if we had an average number of connectivity, then this is going to give us a modularity score of 0. If we have a lot more than is expected, then this modularity score is going to go up. So this seems like a pretty reasonable way to say, do we have a higher amount of connectivity within each community than expected? And the expected is going to be, just to be clear, it is going to be dependent on the degree. So this is not just a global average number, but it depends on the degree of the degrees in your graph. So obviously some graphs just in general have higher degree and some graphs have lower degree overall, right? So you have to have an expected number of edges based on the degrees. So the question is then, well, how do you come up with what the expected number of edges is? And so basically we can come up with a null model. We can come up and say, what is a, if you didn't have any clustering, what is a reasonable expectation? And so the way we can do this is basically we can just say, well, what if we took all the nodes, we kept their degree numbers, but we just randomized where all the edges are connecting to? Okay, so that should have no inherent clustering affinity, right? Because we're just randomizing things. So there's a certain amount of clustering that will just naturally happen if you have high degrees, but it won't be any more than just random because we're randomly assigning these. And if you really want to just do like randomization, like with replacement, then that means that you might wind up connecting node I to node J more than once. So that's why they say, okay, we're actually going to consider this a multigraph. So we're going to allow multiple edges between the same two nodes. So if you do this, then you can do some very simple math. You can sort of simply say like, okay, well, you know, if I is degree 3, then I have 3 chances to connect to any, other node, and, the number of the odds that I connect to any particular node is basically based on the degree of that node divided by the sum of the degrees of everything. And so if you do this math, then basically you say, oh, okay, here's the odds. It's the degree of I times the degree of the other node j divided by 2m, m being the number of edges. So, okay, so basically now I have a formula for the number of expected edges between nodes. I can take this and I can do a little bit more work with it. And then ultimately, I can show that, yeah, in fact, the expected number of edges in a multi-graph, if I just randomly do things and you do all the math and say, okay, so now basically I have this null model where basically I use this thing of degree of node A, degree of node B, divided by 2m, and that'll tell me. And I can do this for the whole graph, but I can do this for each subgraph S that are my communities. Okay, I just caught up with the chat and I apologize. I don't know how old these chat messages are. Somebody said, does edge length have any meaning in these graphs? I apologize. I only just saw this, so I don't know how long ago you asked this, but in the slides, edge length is meant to communicate something to you visually, but it's not indicating that we actually have any real ground truth data. Okay, it's just the graphs are drawn that way, so they look nice. But in the actual information, we're generally thinking of these as unweighted, undirected graphs. So it's basically a simple adjacency matrix with just ones and zeros. Okay, so in this null model, we have both the distribution of degrees and the total number of edges preserved, but we now have a way of sort of assessing what randomly do we think is the expected number of edges. So then we can use that. And so we calculate this modularity. So this Q, basically we're going to say, okay, remember, it's number of edges actually in the group minus the expected number of edges. So this kind of triple, summation, which is a little bit of a, pain in the neck, but in the end, it's not really that bad, because you're basically saying for all pairs of nodes I and j, that's the rightmost two summations. Okay, so for every pair I and j, basically we have this, aij, that's using the adjacency matrix, and then we're subtracting the expected number, which is the degrees divided by 2m. So we're going to do that, and then we have to do that for every community. So that's what this leftmost, this third summation is. So if we say we have 4 communities, then we're going to sum over all 4 communities, all the possible pairs of nodes. If we do this, then we're going to get this modularity score. But what we really want is we'd like to have it on a nice uniform scale. So if we divide it by 2m, then what'll turn out is the maximum possible Q value will be 1, and the minimum possible Q value will be -1. So we have this nice, now we have this nice uniform range, and so you can kind of talk about numbers, and they're not graph specific. And so in fact, you can say something like, yeah, if you get a score between positive 0.3 and 0.7, then that's showing quite a bit of community structure, as opposed to just like splat. You put down these nodes and you had some sort of random connectivity between them. So now we've got our modularity metric Q. So we can calculate this for any graph given a particular community definition, how we've partitioned it, this big S. So I think this is just recapping what I said. So again, in the green box, you see this is just within each partition, you sum over all pairs of nodes. So does community structure mean density? It's sort of akin to density, because we're really trying to measure the density of edges connecting nodes within. But the problem is that it's like, I don't know, it's exponential or factorial or something crazy like that. If you just simply said, here's 100 nodes divided into 4 communities, how many ways are there to divide it into 4 communities? There's a gajillion ways you can do it. And so, so ultimately what we want is we want densely connected communities. And depending on your definition, you either only measure the density of the connectivity, which is what modularity does. Modularity does not explicitly measure the number of edges that go between different communities. So it's sort of implicit. The higher the density within your communities, given a fixed total number of edges to begin with, in order to get as many as possible into each community, you have to then indirectly minimize the number of edges that are going out between communities. So if you actually had a graph that had disconnected components, if you made each of those weakly connected components a separate community, then you would have 0 edges going between communities. All the edges would be within communities. But in a fully connected graph, then you're always going to have some edges that are going out in between. But so I say that, but at the same time, I don't think technically speaking, density has a formal definition in graphs. Not like in physics, you know, there's a certain definition of density. But ultimately, that's what we'd like. We'd like to see this dense connectivity within each community. And the number of communities isn't defined in advance. So not only do you want dense, but then you have to decide, well, should this be 4 communities or should really be 6 or 8 or maybe 3? So makes it a very, very hard problem. All right, so that is our modularity metric. And again, we're just simply saying the number of edges within each community compared to just sort of the default, the randomized version of that is what we're going to measure. And we're not counting the number of communities. It's independent of the size of the communities. And we're not directly penalizing it for the number of edges between communities. And I'll just note also here that if you have a node that's by itself, assuming that we don't have self edges, then you know, there cannot be any edges within the community. So this first term is always going to be 0. So you can have a 0 or you're going to have a negative number, but you're never going to be able to have a positive modularity score from having nodes just sitting there by themselves. All right. So that's the second piece that we had, which is defining a metric. Any questions? All right. So I mentioned earlier, we're only going to talk about modularity here today, but there are other slightly different ways I've seen in the literature that people measure community. And if you measure it slightly differently, then of course, if you optimize for that metric, you may potentially get slightly different, you know, optimal community structure. So it's kind of interesting to see that there are a number of papers that actually say there is no formal definition of community that everybody agrees on. So in this paper, this is how we're going to define community, and then let me show you why, you know, my algorithm works or whatever.
Ted, can I ask a question before you go further?
Please.
Yeah. This AIJ, how did you calculate? Can you show it again? I missed that part.
Yes. So this is coming from the adjacency matrix.
Oh, okay, thank you.
So the adjacency matrix is 1 or 0, depending on whether there is an edge between I and J. Thanks. Anything else? All right. So then, so then for me, this was the part that I was looking forward to. It's like, so how do people come up with algorithms to find these optimal community structures? So the first thing I will say is these are not the global optimal community structures. These algorithms are heuristics that are finding very good partitions, but they're not perfect one. So we're going to talk about the Louvain algorithm. And specifically, if you run Louvain modularity multiple times, you will get slightly different answers potentially. Okay, so you just run it with different random number seeds, and you're going to get different answers. So this is a very efficient algorithm, and it's a very good algorithm. It's pretty much implemented everywhere. It's in Network X, it's in Neo4j, it's everywhere. But just to be clear, this is not a global optimum. So what this algorithm is it's a greedy heuristic. It has a very fast n log n approximately running time. It's a little bit hard to define exactly what the runtime is. We've been talking about unweighted, undirected graphs, but it actually supports weighted graphs. It actually requires that it can handle weighted graphs as part of the way the algorithm works, which we'll see. And then an interesting thing about it is that this is actually a hierarchical algorithm. So it is going to output multiple levels of communities. So the final level is going to be fewer large communities, but you'll actually see the earlier levels in this algorithm actually will have more smaller communities. And back in the second session, when we talked about sort of handcrafted features, so this is one of the things that you can do is that if you're doing machine learning, so most of the time the communities, whether it's like k-means in tabular data or a community detection algorithm on a graph, generally speaking, the community is not the end result, what you're looking for. You're using communities because they are useful features for some additional thing that you're going to do. And so one of the nice things about the Louvain algorithm is that you don't have to necessarily choose which level in the hierarchy you're going to use. You can just use all of them. You can say if the Louvain algorithm had 5 levels in the hierarchy, I'm just going to use all 5 of them as 5 different features. And so some of them are going to give you bigger structure and some of them are going to give you smaller structure. But since it is a very fast algorithm, that I think that's one of the reasons why you see it's widely implemented, and it does work really well. So high-level overview, what is this algorithm going to do? It's going to greedily maximize the modularity as best it can, and it's going to do it in 2 phases. It's going to have 2 phases. So the first phase, it's basically going to look at the graph and it's going to say, what if I move this node to a new community, do all of that. And then once it's maximized that, then what it does is it takes each of the communities and it treats it as now a super node in a higher level graph. So if the original phase 1 identified 10 communities, it's then going to run its own algorithm on a new graph that has just 10 nodes. But in this case, the nodes will be weighted, and we'll see the details. So it's not just a vanilla 10 node graph, but it's weighted based on the community size and membership from the first phase. And then it just repeats this. And then basically it gets to the point where it says, I now have 3 communities, and it can't find any way to increase the modularity score. That's when the algorithm stops. So that at a high level is what it's doing. So let's kind of go into the details. So the Louvain algorithm works on weighted graphs, but you can obviously always run it unweighted, just all weights are 1. And yeah, I think this is basically saying stuff that I already said. So we're gonna do this grouping into communities, and we're increasing the modularity score. All right, so phase 1, how does it work? Yes. So oftentimes in a problem, you do have weighted edges, but let's say you're doing a social network. You might not. You might just say these people are friends, and you might not have a weight. It's also possible that you do use some particular data that you have to say, I'm not going to treat all friends as equal. I'm going to have some have higher weight, some have lower weight, but you know, both are possible depending on your problem. Okay, so it's pretty straightforward. What the Louvain algorithm does is basically you have to assign some sort of ordering to the nodes, and it's going to loop through all the nodes. Okay, it could just be a random thing based on you just have some random node IDs, and it's going to go in order. But it does need to go through, and this is where if it went through in a different order, hypothetically, you might get a slightly different answer. But in practice, when people have tested it, if you change the ordering, the results have very similar community structure and very similar modularity scores. So what we're going to do is we're going to look at one node at a time, and we're going to say, okay, I'm a node. Let's say I have 10 neighbors. What if I took my node and I put myself in the same community as each of those 10 other neighbors? All right. Now, of course, if you're already in the community with some of them, then it doesn't need to do any work. But that's sort of a no-op. But to the extent that any of your neighbors are in a different community, you can say, what if I put this node in that community instead of my community? And what you want to do is you want to calculate, does the modularity score go up? And if so, how much? And then basically you're going to look for the max of all 10 of those possibilities. So some of them may be zeros, some of them could be bad, they could be negative. But if there's one that's positive, then you're going to take the highest one and you're going to say, I'm now moving node I to be in that community. And you do this one at a time for every single node in your graph. And then one thing that's not clear on this slide that I just wanted to highlight is that you have to actually repeat this multiple times. So if you have a graph with 100,000 nodes, you're going to go through all 100,000, and then you're going to start at the beginning and you're going to go again. And you're going to start back at node 0, and you're going to go through all 100,000. And basically, you keep going through every single node until you get to the point where you did a complete pass of all 100,000 nodes and you didn't move a single one. So at that point, then you say, I can't move any one node and get a better modularity score, so I am done with phase 1. And so this is where, again, it's a greedy algorithm, and you could ask the question, like, hypothetically, what if instead of moving one node at a time, you move 2 nodes at a time, or 3, or whatever, you know? And yes, it is theoretically possible that you could get a better modularity score by doing some of those kinds of moves. It doesn't consider that. And so that's why this is not the global optimum. This is just a very, very good heuristic for finding a very, very good local optimum. All right, so does that make sense in terms of phase 1? We're just going through the nodes one at a time, looping, and you only need to consider your neighbors when you're deciding, you know, where else. You don't have to, you know, look at all possible other nodes. Just your neighbors are the only ones that you consider for moving into new community. All right. So once we've done that and we finished the first phase 1, this is the first community map. This will be part of the output. This is the structure that has the most communities that are the smallest. Then we're gonna, in phase 2, oh, sorry, whole piece first. Okay. So we want to know, does the modularity go up or down? How exactly do we calculate that, right? So it turns out that you can calculate it relatively efficiently. So we know how to calculate the modularity score. So worst case, you could brute force it. You could simply say, okay, if I move I from the community that it's currently in and move it to my neighbor's community, I'm now going to recalculate modularity for the entire partitioning S, but that of course would be super expensive in a large graph. So the idea is, obviously, the only place where modularity might change is whatever community I is already in and then the community that it's going to. So if it's already in community D in this slide, if it's already in community D and we're moving it to community C, then in fact, instead of doing it in one fell swoop, we can think of it as actually being 2 operations. We can think of, okay, I starts out in community D. We're going to remove it and place it by itself in its own community of 1. Then we're going to go and we're going to move I into community C. And it turns out that removing I from a community is the exact inverse of adding I to a community. So if you know how to calculate the modularity for adding something to community, it's the exact same math, but just with a minus sign to remove it from a community. So if we think of it as these two, with this intermediate step as these two things, then this complex operation of change in modularity of moving I from community D to C just becomes the sum of these two individual modularity changes, removing from D, adding to C. And it turns out that that's a much simpler way to think of it. So first, what's the modularity within groups? So we're gonna look at the change in modularity for adding I to C. What's the modularity of C? Well, we've defined that. That's the sum of all the weights within this community C divided by the expected. All right, and so basically, if we use this shorthand notation where we call sigma in is the sum of all the things that are already inside C, okay, and sigma total is the sum of all the weights, so the sum of the degrees. Okay, so we're going to use these two shorthands on the next slide. Sigma in, just the edges inside. Sigma total is the sum of the degrees. Then we can basically say, okay, the modularity of community C is, again, you've got this sum over all pairs of I and J that are in the community. We're going to have this, adjacency, which is 1 or 0, minus that. Actually, in this case, now it's weighted, so this doesn't have to be a 1. So it's either a weight or a 0. And then again, we said we're gonna subtract the expected thing. So if you kind of do the math, then basically you can simplify it to say it's got these two terms, that sigma in that we defined over 2m and sigma total over 2m squared. All right, fine. So if that's the formula, then basically we can say we've got, I think I've pretty much covered this, but so now we're going to add I, which means we're going to get some new nodes within the new C that includes nodes from I. And we're going to have some new potential out nodes, which are the links from I. So basically now we just need to consider things from I that are inside and things that are not. So we have this notation now we're adding, which is the degree of I that's inside versus the total degree of I, which is the standard notation case of I. So some of you may not care about the math, but if you're interested, so then basically we do this, we can basically see when you take this isolated I, you move it in, then basically our term, we're supposed to be subtracting our degree of connectivity inside goes up by this ki in, and the total amount goes up by ki. And so then this is our new formula, the two things in the green boxes. So this is how much our modularity has changed. And so then to summarize, I believe we have one more slide. So we just have this formula that's in the first bullet. It might look a little bit, it's not the shortest formula, but it's not so bad. And the main point is that you're not really calculating a whole bunch of things over and over again. This is a very localized calculation that just deals with I and the community. And so this is the formula for what is the change in modularity for adding I to C. And basically, if you did the same thing, you looked at D without I, and then you could say, what's the modularity for adding I? And then if you put a minus sign in front of it, then that would be the same thing as the modularity change for removing I. So this is just to show you that, like, behind the scenes, the math that you need to do for each of these things where you test, what if I added I to this community, to that one, to that one, to that one? It's a relatively inexpensive calculation. And so you do this k times, up to k times for every node, and you do it for every node, and then you repeat that whole process multiple times. And typically you're not going to repeat it. It's not going to be like an n squared kind of a thing. You're going to repeat it, a handful of times. You're going to pass through all the nodes, but it's not. Graph gets bigger the number of times you need to repeat this doesn't necessarily grow. And so that's why it's not really considered an n squared kind of a running time. All right, so now we've said we can calculate relatively fast the modularity change for each one of these things that we want to test. And then we're going to run that loop. So in summary, for every node, we find the best community, we calculate the change, and then we actually literally move I to that new community. And so for the rest of the iterations, when we're considering things, we no longer think about where I used to be. We only consider where I now is, which is in its new home, in its new community, C prime. And as I said, you keep doing this until you do an entire pass over all n nodes, and there's not a single one that you can move to improve the modularity. Then you're done with phase one. So phase two, what we do is we say, okay, we've finished phase one, we found 10 communities. We're now going to create a new graph of these 10 super nodes. And what we're going to do is we're basically going to use the number of links between communities as the edge weight between these two super nodes. In addition to that, we need to know something about within each node. And so we're going to change it to allow for each super node, we're going to have a self edge, which is the weight of all the nodes of the original nodes that were within that community inside. And so this way, we're sort of preserving the inside strength of each of these super nodes compared to the outbound strength between the communities, between the super nodes. So if we do this, then really now we can repeat phase one on this set of super nodes. The only difference is the original graph, we never had self edges from a node to itself. So when we were looking at the adjacency graph of the original thing, the main diagonal was all zeros because we had no self edges. I guess technically you could have allowed it, but I don't think of like, I'm Facebook friends with myself. I don't think of it like that way. So typically there's zeros on the main diagonal, but on these later rounds, you do have large numbers on the main diagonal of the adjacency graph. And so in this case, you can imagine that you have these three communities. So you create these three super nodes, and you're just going to repeat the algorithm. Now, obviously, the number of communities tends to be quite small. And so the later rounds after you do phase two, they tend to shrink really, really fast. So the running time on the second round is going to be much, much smaller. So here's a nice diagram. So imagine this original graph, the nodes are all gray and you don't really know what the communities are. And after phase one, you decide there's 4 communities, the purple, the orange, the blue, and the green. So then in step 2, you basically say, I'm going to create this new graph that has these additional self edges. You can see the weights are written down on here. And so then now we're just going to repeat phase one, but on a graph with only 4 nodes. And it finds 2 communities. In this case, it's calling them purple and green again. And so then voila, we now have. So then the algorithm would technically run again, a third pass on just this 2 node thing. And it would say, nope, I don't want to merge them or whatever. And so I'm done. And so then just a quick note, reminder. So the Louvain algorithm is going to say, ultimately, I have 2 communities, but it's also going to have, again, multiple outputs. And so if you can ask for not just the final set, but you can also ask for the earlier ones. And so then you'll have more communities that are smaller. And so in theory, if like this particular, node 0 in this algorithm, you could say, what are the communities for it? And it would say, I don't have community names, but basically, oh, node 0 was in big purple and little purple. And then maybe node 3 was in big purple and little orange, and so on and so forth. And so then you could use those as features for some other machine learning algorithm. So here's an example. Belgium, if you don't know, has a bunch of Dutch-speaking people, has a bunch of French-speaking people. And so no surprise, the French-speaking people tend to talk to each other, the Dutch-speaking people tend to talk to each other, and then there is a cluster. There's some connectivity in between, but some people do speak both French and Dutch, and they talk to each other. So it's very easy to then partition this phone network into two communities. All right, so here's our summary. What does it say here? We're partitioning the graph into communities. These are disjoint communities. You do not need to tell Louvain the number of communities. It will automatically determine that. It's a greedy algorithm. It runs fast, can run on very large networks, and people don't, to my knowledge, people do not tend to run it more than once. If you run it more than once, you will get slightly different answers, but they're similar enough that I think people don't do that. They don't average multiple runs of Louvain. You just run it once, and you either use the final communities, or you say, I'm going to take a vector and I'm going to use multiple layers of the communities. There are other algorithms you might see, like label propagation and other things. I think generally speaking, Louvain is considered to be more advanced, to do a better job than those other algorithms. But again, worst case scenario, if you were trying to come up with features, for some machine learning model, hypothetically, you could do a GNN, and you could also do this community detection using Louvain. And theoretically, you could say, yeah, and I'll do label propagation. I'll throw in another, feature for that. And maybe my model will just ignore it because it's not a very useful feature. Maybe ultimately you decide, you find out that, like, the feature importance on it is super low, so you remove it, but doesn't necessarily hurt if, say, you're building a gradient boosting model to just throw in that feature and then see if it likes it or not. All right, any questions about Louvain? All right.
I just really enjoyed the nesting nature of it. With the thought that, like, you take it down to its absolute lowest level, but then if you want, like, you could just step back up and get a little bit more granularity of understanding.
Yeah, I don't know if other people know. So, like, for tabular data, we have hierarchical clustering algorithms, and I haven't done a whole lot. I don't tend to use the different levels of the dendrogram that much, but you can definitely think of it in terms of, and in that case, the hierarchical clustering will generally, it'll be everything from all the way until it's just one giant cluster, all the way down to the smallest clusters. So Louvain is similar in that way, is that you can look at it from the different levels, and I think depending on your problem, you may find that a particular level, it may not be the final level, the largest clusters. It may be that you want a slightly smaller cluster size for the particular thing that you're trying to study. All right, anything else? Any other comments, questions? All right. So our final topic is overlapping communities. So what we just did with Louvain will only find disjoint communities. And so the idea is that, well, in reality, like, if you have friends, they're not necessarily divided into disjoint communities. Somebody might actually be a coworker and also be someone you play basketball with, right? So here's an example. I don't know if this is actual real data. I think it is, but basically, like, okay, here's this Stanford grad student, and here are his friends, and can you figure out what the social communities are? If you tried to do disjoint communities, it would probably work. Like, I feel like there's sort of something here on the right and something on the bottom. But if you look at the ground truth labels, what it actually is that there's like 4 clusters here, 2 different sports he plays, people he works with, people he went to high school with. And you can see some people are in 2 or 3 categories. And then there's some people who are only in 1. But so probably I would say that this particular way of looking at it, intuitively, it seems to me, this is a better more reasonable way of thinking about his friends than requiring it to be some number of disjoint communities. And so if the whatever the combinatorial possibilities for disjoint groups was large, then for overlapping ones, it's just going to be even larger, right? So you can imagine that it's taken a while before people really started tackling this problem. Here's another example. This is protein-protein interactions. Proteins don't only just do one thing. Sometimes they do multiple things. They interact in different kinds of reactions. And so here's, based on the research people have done, here's sort of where you can see overlaps. And in some cases, it looks like things might even be subsets of another community. So it's not just that they have an, like these two, there's an, my little thing keeps popping up. So like these two, they have a small intersection right here, maybe, but it looks like over here, this one might be completely a subset of the bigger oval. Okay, so we're going to talk about primarily one algorithm. NOCD is the neural overlapping community detection algorithm. And actually, if you look at the links, Ryan, maybe you can post the link to our GitHub. If you look at the bottom of the resources, there's the Stanford slides, and there's also YouTube videos. So the YouTube video is actually slightly older than the slides right now. And so you'll see Professor Leskovich is talking about the big clam algorithm that actually he was part of developing. And so I'm going to talk a little bit about big clam as well, and then NOCD differs a little bit from big clam at the very end, but the beginning part of it is sort of the same assumptions. So there are other overlapping community algorithms out there. The way both of these algorithms work is we're going to use this affiliation graph model, AGM. So basically, you're going to think of this from a generative perspective. So I have this graph, and what if, as opposed to just dealing with this as reality, what if we were generating a synthetic graph? We have a topic coming up later, which is about generating realistic graphs, okay? So this is a very simple model for generating graphs. And so you say, what if up front I told you that there were a certain number of communities? Then how would you decide which which nodes would be connected to which other nodes based on if you knew this community membership? All right, so here's how we're going to do it. Here we just have two communities, you see A and B, and we just have a very simple thing here where we have a probability associated with community A and a probability associated with community B. And we just say, for every pair of nodes in community A, this probability A is the random chance that those two are connected. And for every node in probability B, community B, the second probability is. But what you can see then is if you happen to belong to two communities, you are going to have a higher chance of being connected, because we're going to sort of flip that coin once for community A, once for community B. And so if you're in enough communities in common, then the odds of you being connected are going to get very close to 1, because we're going to just keep flipping this coin over and over and over and over again. And so in the literature, you'll see this kind of referred to as like a Bernoulli-Poisson model, and you can imagine where the Bernoulli comes in, right? Because basically it's either probability P or 1 minus P that you're not connected, but you're repeating this, and so that's where the Poisson comes in for random models. All right, so a little bit of terminology here. Given parameters V, the vertices, C is the communities, M is the number of edges, total number of edges, and a list of probabilities associated with each community, P sub C. We're gonna basically flip a coin, and so what you can see then is the probability that sorry, I've got this little thing covering my screen. The probability that we're not connected based on any given group is 1 minus P sub C, okay? And if you're in multiple communities, then you have to multiply all of those together. And so the odds of you being connected then is 1 minus the chance of you missing on all of those coin flips. So it's this expression here at the bottom, 1 minus the product of all of the 1 minus probabilities. So a little bit of a pain because of all the 1 minuses, but you can calculate the odds for every pair of nodes that they are connected or that they're not connected. Okay, cool. So if we were generating a graph randomly based on certain communities with this model, this is the AGM model, that there's just this fixed probability. Now, obviously, in reality, the probability might not be uniform across the whole community, but this is our generative models. We're assuming even uniform probability of any 2 nodes within that community being connected. So now we can say, okay, we can think of that model will generate graphs that naturally have overlapping community properties. So what we want to do is we want to now go in the reverse direction. Sorry, I jumped ahead. One more concept. So in terms of the expressive power of this AGM model, it's actually pretty good because this model can actually generate graphs that are disjoint. They don't have to have anything in common. It can generate communities in a graph that are overlapping, which is the lower right, over here, A and B. And it can actually even have nested communities. So like I was pointing out on that protein one, we see different ways that they're related. And so absolutely, a lot of the proteins, mostly 2 communities, don't overlap. They might overlap with 1 or 2 other ones, but in general, if there's 50 communities, you're only overlapping with 1 or 2, and there's 48 that you don't. And so this AGM model seems plausible because it can generate all of these different possibilities. So what we want to do, this double-sided arrow, it's not the easiest to see, is that, yeah, AGM model says, if you define these communities and probabilities, I could randomly generate graphs for you. But what we really want to do is we want to take an existing graph and we want to say, what is the AGM model that would best fit this particular graph? So in other words, can I derive sort of these probabilities and then see what is the coloring, what is the actual community assignments that best explain this? So if we kind of just think about general machine learning, how do you fit a linear regression? How do you fit a logistic regression or whatever? Basically, one view of it, right, is that you have these parameters, we'll call them theta, and what you're trying to do is you're trying to find the theta that best explain, your particular actual data. So in a linear regression, you can think of it as like least squares, but you can also think of it from the perspective of maximum likelihood. Okay, and so if you're familiar with that, so if you do maximum likelihood, you get the exact same answer as if you think of it the other way from a least squares perspective. So we want to find the parameters that maximize the likelihood that our resultant graph actually came from that particular model. The one thing that I haven't quite figured out from this literature is you do need to pick the number of communities in advance. You do need to specify the number of communities. And it's not clear to me that I think it might work where if you pick a number that's too big, then you just find you get a bunch of communities with only 1 node or empty communities. And so like if there are actually only 4 communities, if you did 6, I think these algorithms might work, but I'm just not 100% sure. I haven't seen anything definitive in the literature that says, how do you set the number of communities? But this AGM model where you have a probability associated with each community, you do have to define up front how many communities. So that's what we're going to do here is we're going to do maximum likelihood. On the slides, there's sort of this explanation. For those of you who are familiar with maximum likelihood, you don't really, there's nothing new here, okay? And so if any of this notation seems a little confusing, just go by your normal understanding of maximum likelihood. But so basically, you can imagine like a simple graph where you've got, you've got just two clusters and they have this slight overlap in it. So imagine that there's this group of people who are in both and they're highly connected. Okay, if you took those people and you said they're only in one community, one cluster, it would be very unlikely that you would get this particular graph with such a high degree of connectivity, because the high degree of connectivity is generally associated with being in multiple communities. And so that's intuitively, that's how like maximum likelihood, sort of works, intuitively in terms of where you see higher connectivity, it's going to have to predict that these people are in multiple communities. So we can use a gradient ascent, gradient descent type of iterative optimization in order to do maximum likelihood. So what we're going to do is we're going to define this matrix F. And this slide doesn't really explain, what F is exactly, but basically F is going to have, I get the rows and the columns confused, but basically it's going to have a column for every node in your graph. So one dimension of F is going to be n, okay? And the other is going to be the number of communities. So this is going to be a rectangular, it's not going to be a square matrix. And this F is basically going to be used in our AGM model to randomly generate the graph, and then we can basically see what is the maximum likelihood of all these parameters theta inside this matrix F that would give us this particular graph. And then once you do that, you can then basically set a threshold. And you can say, if this value is above this threshold, then we decide that, yes, this particular node is in that particular community. So if it's one row per community, then each column is a node, and you just decide based on this, say my cutoff was 0.2. So then this first node is in this community 1, but not the others. This guy's not in any, so maybe I picked too high of a cutoff. Let's pick 0.15. And the second node is in the second community only. This one's in the third community only. This one's not in any, something like that. All right, so it turns out that we need a little bit more to make all of this work. What we need to do is we need to relax this AGM model a little bit, and now we need to say that these memberships have strengths. Okay, so before we were thinking of all memberships as being equal, now we're actually going to change it a little bit, and we're going to say that they have a strength. Some people have higher and lower values of community membership. And so what we have here is there's going to be this non-negative matrix. These are all positive numbers in F. And what we're going to do is we're going to do non-negative matrix factorization. But in this case, we're just doing maximum likelihood in order to find this. So I'm not going to go into all the math, but basically you can figure out that the probability of things being connected, what we said was in the original model was this Bernoulli thing where we flip a coin, but now we're using these strengths. So we're using the values that are in these columns of the F matrix. So this is the U column of F, this is the V column, and then basically it's based on a particular community. So we're gonna do the dot product of these, and this will then sum up over all the communities they have in common, blah blah blah. And we'll do this thing that we love to do where we take e to the whatever, negative power. So I'm not going to go through all the math, but if you do this, then basically now we have a nice formulation, which basically says the higher the strength of two nodes belonging to a community in common, the higher the probability they're going to be connected. That's ultimately what we want. We use this particular red formula here, and we chug things along. Then we have some other things. We say, well, okay, the probability they're connected by at least one community, blah, blah, blah. We got to do the product. That's why my screen's getting covered, but that's why you have this big pi product for all the communities they have in common, blah, blah, blah. You do this, you expand all of this, And you end up with this relatively small formula here, 1 minus e to the negative, again, column F for node U transpose times column F for node V, the dot product. All right, so far this part is, I've kind of blitzed through a little bit of the math, but this part is common to both Big Clam and the NOCD algorithm. So what Big Clam does is it says we're just going to do the actual maximum likelihood algorithm, and we're going to try and find all the values for that rectangular matrix F that maximize the likelihood that this graph was generated by these particular values. And in NOCD, what they did is they said, well, we can actually find a different way of finding these particular values. So there's a little bit more in the slides here. It talks about like, okay, I gotta, again, the probability, you're doing a lot of multiplication of probabilities, again, because people are in multiple communities and you multiply the probabilities. But if you do all of this stuff, then ultimately you get these formulas. And on one of the slides, it explains that we generally speaking talk in terms of log likelihoods because we have very small probabilities and they're numerically unstable. And so if you have, 0.001 times another 0.001 times another point, you get some really small numbers. But in the log space, you don't have as many problems with sort of underflow, kind of errors. So we define this as our objective. This is our loss function. Okay, so Big Clam would have just said, let's treat this as like whatever, 16 parameters, let's optimize this. NOCD says, no, I have a smarter way that I can do this. I'm actually now going to use a GNN. We've defined graph neural networks. This is what we spent the last 3 sessions talking about. Let's actually use one. And in the graph neural network, remember, it's message passing between adjacent nodes. So there's this great inductive bias that the graph neural network, you want nodes that are adjacent to each other, that are highly connected, to be in the same community. So therefore, this GNN model ought to have a really nice inductive bias, and it does. So what they do is they build a fairly simple GNN. I think it's, so this is the formal math for it, but I mean, basically what they're just saying, this is a graph convolutional network. So this is the really simple kind, where all you do is you take the inputs from your neighbors and you multiply it by a weight matrix. So the first layer is represented in here, where you take the node features and you multiply it by a weight matrix. They run it through ReLU, I think, I'm not sure, but they run it through a activation function, and then they do a second pass. So this is only a 2-layer deep GNN. It's very simple, and it's the simplest kind of GNN, the convolutional GNN. And then just a quick note here: this A tilde is this scaled adjacency matrix where you multiply by 1 over the number of degrees. So you can do the math and you can do all this, and then basically they run the GNN over this, and it ends up, it kicks butt. It's like, on most things it beats all the other algorithms. In here they use X, which is your actual node features. If you don't have node features, then they just use the adjacency matrix. They don't have any special features. But so again, it's really cool because now not only can you use the structure of the graph, but you can even use the node features in this NOCD model. So it turns out that it works really well. There's an optimization that happens in here because at one point they're calculating edges that you're not connected to, and so they can cache something for all the edges, and that makes the algorithm run a lot faster. They also then weight the contribution of the loss from edges you're connected to edges you're not connected to. You do want to optimize both of these. I'm sorry, I don't know if you can tell, I'm running out of time, and also I don't know that people want to, so I'll post the slides, you can go through these, but basically, so that this is your loss function, and they're going to train this very small 2-layer CNN. the cool thing about this is you don't necessarily need to retrain this GNN on every time you run it. You actually can train it on a certain amount of data, and then you can freeze the weights, and you can use this 2-layer GNN in the NOCD algorithm on new graphs that it's not seen before. So that's actually pretty cool. And then finally, we just have an example here. You've got 9 nodes. If you tell it you want 2 communities, then it's going to output for each node what are the weights for each of them, and they use a cutoff just of 0.5. So if you're over 0.5, then say yes, that node's in the community. If it's less than 0.5, then no, they're not. And so for this, you can see this is the algorithm, and then the green and the blue are the ones at over 0.5. And so it actually kind of predicted these 2 structures, and the red nodes are the ones where the nodes in both. All right, so I kind of blitzed through a little bit of the math and the stuff at the end, but I think the thing that's very cool is people have started to look at overlapping communities, and Big Clam worked a little better than a lot of the other algorithms, but then ultimately they said, no, we use the graph neural network, and it had dramatic improvements over these other algorithms. So I know I'm at time. Some people have to drop. Any questions about overlapping community detection?
What is a computational complexity?
I'm not sure. So basically, this is a pretty fast algorithm as they do this caching trick. And then the thing is, the training the neural network, like I said, you don't have to train it every time you run it. So you can actually pre-train it and freeze the weights. So that doesn't necessarily need to be included. So for example, if you're just using the adjacency matrix, then you can train a model on multiple graphs and then freeze it, and then you can just input it. If you're going to use the features, then of course you have to train it on graphs that have those same features, and so then that has to be added to your cost. But both Big Clam and NOCD are, I don't know the details, but they are algorithms that scale very well. That's inherent to when people are looking for algorithms, they're looking for ones that can scale. So I do know that, like, I have links here to the papers, and you can see like they've run these on like whatever, 50 million node graphs to test the algorithms and stuff like that. Anything else? All right, so just a quick recap. So we said community structure is natural to networks. And the thing we found is that what you want to know are sort of the socially strong edges, and it turns out that those are exactly the same as the tightly connected ones. So we can use modularity. There are other metrics. Louvain will do disjoint communities, roughly n log n running time, very fast. Not sure the running time for NOCD, but it is basically it's going to be pretty fast. I mean, just 2 passes over n nodes for the neural network part, and then it's basically going to be predicting your F matrix, and then they say that you don't have to tune it a lot. They can just use 0.5 generically as a cutoff. So I don't know. It's possible that NOCD is even linear. I mean, it has a fairly high constant, but it might even be linear. Because it's only using a small 2-layer GCN. And so then I have links to the papers if you want to see the actual Louvain algorithm, or Big Clam, or the NOCD algorithm. And there's also a poster from when they presented this at the KDD conference. And if you're not used to reading machine learning papers, then it might be a little easier to start with the poster as opposed to going straight into the paper on arXiv. So that's it for today. Thanks everybody for sticking with it. So next session in 2 weeks, we're going to talk about another use case. So GNNs for recommender systems. Then I haven't read anything really about generative models. So I'm really looking forward to, we're going to talk about generative models. And then we got some other special topics. Knowledge graphs is kind of a big thing we need to talk about.